Hey team, time for video 23? Yeah, that's right, because I skipped video 22. I meant to do that. I really did, actually. I'm going to get rid of these graphs from the last video. So we don't really need them anymore, and we're about to see a different kind of graph. I'm going to make this window a little... Oh, I see. I have to move myself down there before I can deal with this. Hello? That should be able to move. No, I want that up there. There we go. Okay. Just wanted to be able to have my environment variables in front of me. So I'm going to switch over from cores.r, where I was working in the correlation video, and move over to bivreg.r, which is a demonstration of bivariate regression. And, oh, excuse me. As you can see, still a little bit froggy. So here's what I want to say about bivariate regression and about regression more generally. So we're starting with bivariate regression, which is actually quite uncommon in the political science context because it's easy to visualize. So it's the only form of regression where you can actually see X and Y, or rather here, X and Y in your perspective. So bivariate literally means two variables, one X, one independent variable, and one Y, one dependent variable. The basic intuition of regression is that we're trying to draw the best line through a scatter plot of X and Y. But there's a very particular definition of what the best line is, and that is the line that minimizes the squared vertical distance from the actual points to the estimated line. So what we're going to do is I'm going to kind of show you by way of an example, moving myself up to the top of the screen again. I'm going to show you by way of an example kind of how this works. So let me first talk through what's in here. So I've got a short preamble. It says bivreg.r, bivariate regression demonstration. I then create a random independent variable. So IV, independent variable, is normally distributed with a mean of 50. Normally distributed, there are 50 observations, the mean is 20, and the standard deviation is 5. I'm going to say that by definition, the dependent variable is equal to, and this should start looking to you like y equals mx plus b from high school. So y equals slope times x plus intercept, plus, in this case, error. So here, dependent variable is equal to 1.5 times the independent variable plus an error term. So we're assuming that the intercept is 0. The error term is, it's mean of 0, relatively small standard deviation. So here's a random independent variable and a dependent variable that we've constructed to be a multiple of the independent variable plus a random error. And because, the multiple, that 1.5, that is the theoretical slope. Amazing. So again, I'm going to put a note in here just to say y equals mx plus b. My hope is that most people are familiar with that notation from high school. So y equal to slope times x plus the intercept. Okay, so I've drawn an independent variable and a dependent variable, and the dependent variable is definitely related to the independent variable. So here is, I'm going to copy and paste this plot, This is just a scatter plot of my two variables. Goes like that. So you can see there's a strong positive relationship. And if we want to, we can check that by going core IV, comma, dv. And it's, 0.9. That's good. We don't usually get 0.9 in political science. That's why I had to make this example up. The next thing I'm going to do is this, line 11. I'm going to make a linear model. So linear regression is easy peasy in R. You don't have to do the math. You just have to know the syntax. And the syntax is, you give your model some name. I've chosen M for model. The function is LM, linear model, dependent variable, tilde, independent variable. And when you have more than one independent variable, that is next week when we get to multiple regression, you're going to start going IV1 plus IV2 plus IV3 plus IV4 plus plus plus. But that's basically it. So it's dependent variable, tilde, one or more independent variables. If there's more than one, there will be plus signs in between. And that's what it is. So we create the model called M. We're going to print a summary of M to the console. And then we're going to do some interesting stuff. We're going to find the estimated intercept. So every linear model produces an estimated intercept and an estimated slope for every slope equals coefficient for every independent variable. In this case, we've only got one independent variable, so estimated intercept is M $coefficients 1, just is, trust me. Estimated coefficients is that. And then we're going to add that line. So AB line is a function that draws a straight line given an intercept and a slope. So let's do all of that. There they are. So now, as you can see, we have some regression results. We have an estimated intercept looking here look under coefficients. The intercept is estimated at 1.13, close-ish. And the coefficient, the slope associated with the independent variable is about 1.47. And that's pretty close, actually, to our designed slope of 1.5. So the difference is due to the error. And the way that linear regression works is by, again, you want to draw the line that minimizes the vertical distances to the line. And so in lines 18 through 20, I've done the following thing, which you might or might not want to try and follow. So for every observation, for I in 1 to the length of independent variable, so again, there are 50 observations. So for I in 1 to 50, I'm going to draw in red the vertical distance from that actual observation to the estimated line. So you can see what's going on here. I'm going to copy that in. There they are. So the red lines are the vertical distances to the estimated line, right? So those are also known, by the way, as residuals, and that's going to become important because residuals are a thing that we're going to use to check regression assumptions. So right now we're using a constructed example so that I can kind of show what those vertical distances look like. But later we're going to actually need to do this with real data. And we'll get into that in the coming days. I'm going to run the whole script a few times so that you can see kind of what happens with different random variables. So let's try this. There you go. There's a different one. So they should all be approximately what we created, right? So the dependent variable is something like 1.5 times the independent variable plus some random error. But it doesn't look the same every time. And in fact, you don't see the same estimated slope or the same estimated intercept every single time. So, but it should be close, right? So 1.52, 1.55, 1.47, 1.54. So you can see that because we're drawing X, or we're drawing the independent variable from a big random normal, that we get sort of something that fairly closely approximates that. If we were to have more observations, we would get values in the estimated coefficients that are more similar to our kind of theoretical values. So let's, instead of 50, let's do 500 for funsies. That's a lot. But as you can see, the intercept is closer to 0. The independent variable is closer to 1.5. Right? And that's really what's going on. You want to, in every case, OLS, ordinary least squares regression, that's least squares because we're actually minimizing the squared distances to the line. But that's the intuition. And the problem, so if the correlation is lower, so let's make one with a much weaker correlation. If the correlation is lower, then the distances to the line are necessarily going to be larger in some cases. That's really large. You know, it's still quite significant. It's clearly a positive relationship, but it is not at all as like clean. There's much more error if there's more variability in the y variable. So that's kind of a theoretical introduction. And the thing to remember about regression is that you're minimizing the squared vertical distances to the line. Okay.